You know, in 3D printing, plastics were the leading edge, but metals, of course, are where the action is. That's where the high-value components are, and that's really where the future is. I'm with John Murray. He's President and CEO of ConceptLaser, Inc. John, densification. The traditional sintering processes, of course, it's been a struggle to really get fully densified parts that are net shape or near net shape. Can you tell me about the ConceptLaser unit we're standing in front of right now?
Well, you hit it right on the head. I mean, for many years, people were trying to get to fully dense metal parts, and that's really the early work that our founder, Frank Herzog, did in Germany, and he struggled for years to get that to work, and finally in 2000 he was successful and started the company. So we're now celebrating 16 years. And the M-Lab, there are two versions of the M-Lab. There's the M-Lab standard machine, and then there's the R version, which stands for reactive metals. So in the reactive version, you can run any steel, any kind of 316, 17.4 maraging steel, and in the R version, you can run the reactive metals such as titanium and aluminum. So it's an architecture that's ATEX compliant. That's our number one concern when you're dealing with metals is safety. So the whole architecture of all our systems is based around strict adherence to those ATEX safety standards.
Now, John, reactive metals has historically been a no-go area for the reasons you mentioned. There's safety reasons. Reactivity is a problem. You're changing metallurgy, in fact. You're applying a lot of energy in a very small space often in these processes.
Right.
What's your process that lets you basically control those variables?
Well, everything's done through the parameters. So we have extensive parameter editor that allows customers to really vary every parameter that our R&D group can work with. So that allows our customers to do a lot of material research. This machine's very popular for that application because you can quickly change materials, go from a titanium to aluminum just in a matter of a short period of time. So that's really been a nice benefit for customers on that side.
Yeah, in terms of changeover, historically, many metal 3D food process companies have talked about a relatively easy changeover. Often in practice, it's not quite that easy. To actually do a changeover involves more than just changing hoppers and backing out the reaction bed.
Absolutely.
Yeah. What's the changeover process like?
The changeover process right behind you is the glove box. So this is a really popular option where customers can actually keep perhaps titanium in one glove box, maybe keep aluminum in another, some kind of steel in a third. And it's just a cartridge system. So you pull that in, you dock it, you're kept in an inert environment at all times. It's an inert environment inside the glove box, inert environment inside the build processor at all times. So you literally can swap these out. You clean the build chamber, which is quite small, so you can do that in a short period of time. And literally with the cartridge process, pull these metals in and out.
Potential applications, aerospace, medical?
Medical's a big one. Dental's also big. So one of our best customers, one of our largest customers is Argon down in San Diego. They're a worldwide company, do incredibly aggressive work, and they have 8 M-Labs that are used for dental applications. They make their own powders, noble alloys, precious alloys. So they're doing amazing work in the digital technology world and a real leader worldwide in that field.
Even with nobles and precious,
Yes, they're running. I think, if I remember right, I think Argon has something like 600 metals that they've been, and alloys that they've been developing. So very aggressive technically, and an exciting company. You find companies that are really aggressive in going after this technology, and then there's kind of like everybody else who's waiting to see what happens. So we like to find those innovators, and this platform's popular because of the flexibility and the open architecture.
Applications like aerospace, for example, of course, the holy grail is total net shape. How close to net shape can we achieve with this technology these days?
Very close. I recently built 2 large helicopter components, about 18 inches long and maybe 6 inches in diameter, very complex, a lot of internal passages for fluid. I had 2 of those built on our large X-line machine, so that's the largest machine in the world, 31.5 by 16 by 20. So we just printed some 6-cylinder engine blocks for a European automaker, so big parts. And when I printed these on the X-line in aluminum, came back, and the worst tolerance over that 18 inches was 8 thousandths, and most were within 3 to 4 thousandths. And that's over a large part. And then we had them X-rayed, and they were grade B all over. So from a casting standpoint, if you're looking for an A356 or an E357 type component, that was an absolute home run.
An engine block is not only a very large part, it's a complex part,
right,
internally and externally, but it's also a part that has to be cast ultimately for volume production.
Right.
So you can't trap or have undercuts in any significant way in a lot of places. So historically, in my experience, 3D printing is in a process where you may 3D print the cores and then go and sand cast or die cast the product this way. You're going directly to a finished 3D printed engine block?
This is a 3D printed engine block. We did 3 of them. One is in a lab, the other 2 are on the road being tested. So it's a good point though, because you could do all kinds of thermal control tricks on that engine block to improve efficiency, right? To get the gas mileage up. But then you have to figure out, can I do this in mass production? Right now, at the current speeds, you couldn't really do that. You wouldn't be able to print these blocks fast enough. But with the factory of tomorrow, which is where we're going with complete automation of the entire process, we're trying to get humans out of the process completely, autonomous vehicles, robots, and I think you're going to see additive metals continually creep into production more and more in the years ahead.
John, I understand that on display you also have some quite large aerospace components. Or I believe I see a gas turbine combustor assembly, in fact, over there.
Yes, exactly. Absolutely. Let's go look.
All right, John, we're holding a couple of Inconel 718 parts. Now that's a classic super alloy used for hot section gas turbine parts.
Absolutely.
Yeah, and these parts are very large.
Very large. These are both built on the X line. You could actually build multiples of those at one time on the X line, being 31 by 16 by 20. So customers are doing these large parts. It's actually a lot of aggressive work in the space sector as well as aerospace and automotive. So that large platform, we did a large transmission case for ZF in Germany, big truck transmission. So again, grade B all over in aluminum, and these are fully dense Inconel parts, whether you're in a run 625 or 718.
How much sort of post machining has been done on these parts we're looking at?
Not much post machining. This was built straight up, so you would have had the support removal on the bottom for this geometry, and that one would have had supports on the bottom. So in these particular geometries, virtually just almost very little post processing. This one's been finish machined, you can see.
Yep.
So people ask me that all the time, is this going to replace CNC? Absolutely not. You're always going to be doing critical surfaces, some finish machining to all these parts. So we're trying to bring those all together with the automation in the factory of tomorrow, where CNC, additive metals, heat treat, because heat treat obviously is a really critical part of the whole process on the mechanical characteristics. So we're going to tie that all together with the factory of tomorrow.
John, how critical is it the support structure? Because we have a very sophisticated and complex part. In the CNC world, it's hard enough to fixture a component. I can't imagine in the 3D world. How do you ensure that you get the part properly supported during the build in a way that you can get the support out after the build?
It takes a certain degree of skill, and it might not necessarily be intuitive up front, but you're really looking at not only securing the part, but that's also a thermal transfer to take heat from the laser and put that down into the platform. So you're really considering several things when you're orienting these parts on the platform. So it's
John, for the sort of medium volume, high value products, the gas turbines come to mind example, where 1,000 units is a large production run.
Right.
Is this technology going to take over significantly? Do you think we're going to see a time when every jet engine that is under the wing of every airplane has a significant number of 3D printing components on it?
Absolutely, absolutely. I think you're going to see that continually creep into automotive. Certainly on the boutique makers, if you're making supercars and you're going to make 100 or 200 of those a year, then additive makes perfect sense. Reduction of tooling costs, reduction of lead time and cost. It's interesting, Airbus, which is a customer of ours that's done a lot of innovation, you look at their paybacks, the lead time reduction up to 80%, non-recurring costs 90%, and then you look at just the cost. It might be 15%, which is significant, but these other things like reducing lead time and getting to market and not having extra stores, reducing 10 parts, making it one part count reduction, those are the things that are really standing out in this technology.
John, we're at ConceptLaser, very bullish on 3D printing for transportation applications.